95% of the businesses face some constraints. A constraint is a hurdle. A constraint is something which limits your activities. For example, a constraint could be raw material. You don't have enough material. That could be a constraint because you cannot produce enough. A constraint could be labor hours, shortage of skilled laborers. A constraint could be money. You don't have enough money to invest. Constraint could be machine hours. So let me tell you, every business faces some type of constraint, which is also known as limiting factors. I have already created a video which is on a single constraint. Means everything else is in abundant supply. What if raw material is not available? Or let's say all other requirement for production is available, but only labor hours are short in supply. So what to do? How to maximize profitability if you have a constraint? I've already created a video on that. But in this video, I'm going to focus on multiple constraint. What if raw materials are scarce in supply? What if labor hours are short? What if demand is not unlimited? There is a constraint for demand. What if you are unable to sell as many units you want? So if a business faces multiple constraints, it can be solved through linear programming. And that is what I'm going to focus on in this video. Hi, I'm the Commerce Specialist. Welcome to my YouTube channel where you'll find videos covering learning outcomes of various academic qualifications and professional certifications, including life-changing business ideas and hacks. So let's jump into the discussion of linear programming. Here I've got a question. It says Delta Company manufactures two products, which is X and Y. And these products goes through two different departments, which is cutting and assembly department. Over here, we are given machine hours. Each unit of X requires 0.06 machine hours in cutting department, and then it goes to assembly department where it requires 0.04 machine hours. So these are machine hours as already stated here. Product Y, first it goes through the cutting department, it requires 0.08 machine hours, and then it goes to assembly department where it requires 0.12 machine hours. Now selling price of a finished units of product X is $1.5 and selling price for product Y is $2. Variable cost of making X is 1.3 and Y is 1.7. This is 1.7. Now comes the constraint. Maximum machine hours are available for each department is 2,400 and you cannot sell more than 13,000 of product Y. So we have three constraints here. The number of hours available in cutting department is 2,400 machine hours. Number of hours available in assembly department is also 2,400 machine hours. So these are two constraints. In each department we have limited machine hours. The third constraint is that we cannot sell more than 13,000 units for product Y. Having said that, what is the objective of the business? The objective of the business is to maximize profit. So guys, in this video, I'm going to talk about how a business can maximize profits even though they have multiple constraints. Constraint relating to shortage of material, shortage of labor hour, capital, expertise, so on and so forth. So now in this question, our main focus is the company would like to maximize profits given the constraints we have. So typical linear programming question starts with certain steps. The very first step is to define the problem. So when we're talking about defining the problem, we need to understand first what are the variables. So we are talking about how much of product X and Y to be produced so that we can maximize contribution, means maximize profitability. So how much of product X and Y to be made and sold in order to maximize contribution. The second step, which is very important here, is to establish constraint. Now you got to be very careful here. If your constraints goes wrong, the entire question will be wrong. So I'm writing the constraints here. For cutting department first, it looks like this: 0.06 X and 0.08 Y. And the maximum machine hours available is this, so I can write an inequality here, equal to less than 2,400 hours. Mind you, this was for cutting department. Now I'm coming to assembly department. The constraint for assembly department will be 0.04x, 0.04 into the number of units made for x plus 0.12 y, and we have less than equal to 2400 machine hours. The next constraint is the demand for product y. So y we can make less than equal to 13,000 units a year, because demand for product y is limited to 13,000, so we can't sell more, so it will be equal to or less than 13,000. And the most important is for x and y, we call it a non-negativity constraints. This is known as a non-negativity constraints, means the production of x or y units cannot be negative, which means we cannot make minus 2,000 units of x or minus 4,000 units of y. So this is also very important. So I have defined the variables, that is the number of units of x and y to be made and sold. That is what we need to know so that we can make maximum contribution, in turns maximum profit. Then we have established the constraints. For cutting department, this is the equation for constraints. For assembly department, 0.04 hours for 1 unit of x into how many units of x plus 0.12 hours of y into the number of units of y, provided we have maximum 2400 hours. Demand for y is not more than 13,000, and x and y, the number of units made for x and y should be more than 0, means some units we should be making. The next step is construction of objective function. This is written like this: maximize contribution, which is C, subject to these constraints. So when we're talking about contribution, contribution is selling price minus variable cost. So for product X, selling price is 1.5, variable cost is 1.3. So contribution will be 0.2x plus selling price for Y is $2 and variable cost is 1.7. So 2 minus 1.7 will be 0.3y. So we have to maximize contribution subject to contribution of x for 1 unit is 0.2 and for y is 0.3. So we need to know how many units of x and how many units of y we should make so that we can make maximum profits, taking care of the constraints as well. Now the next step here is draw constraint on a graph. Now when we are drawing a constraint on a graph, we need to find some points first. How it is done, please have a look. I am taking cutting department first. See, the equation here is, now if I take this equation, I am talking about cutting department. Cutting department. The equation is 0.06x plus 0.08y, and inequalities I can always change into equal sign, is 2400. So I want to know if x is equal to 0, y would be how much? So if I put x equals 0, 0.06 into 0 this will eliminate. Like if x is 0, so it will look like the 0.06 into 0 plus 0.08y is equal to 2400. Obviously anything into 0 will be 0. I am left with 0.08y is equal to 2400, and y will be 0.08 is multiplying. When it goes on the other side, it will divide. So 2400 divided by 0.08. So y will be 30,000 units. Likewise, I would like to know if x is equal to 0, how much is y? Y is 30,000. And if y is equal to 0, how much will x be? So in that case, in this equation, I'll make y as 0. So this will look like this: 0.06x plus 0.08y is equal to 2400. Now I'm making y 0. So 0 into this will eliminate. I'll be left with 0.06x is equal to 2400. X will be 2400 divided by 0.06, and you will get x as 40,000. So I'm going to plot this on the graph here. When x is 0, y is 30,000. Please have a look at this. This is x. When x is 0, y is 30,000. So when x is 0, y is 30,000. And when y is 0, this is y. When y is 0, x is 40,000. X is 40,000 here. So what I can do is I can join these two lines and write here the equation which is for cutting department 0.06x plus 0.08y. 0.06x plus 0.08y is equal to 2400, and this is cutting department. Similarly, I have to find the points for assembly department. So I'm doing it here very quickly. The equation for assembly department is 0.04x plus 0.12y is equal to 2400. Again, we want to know if x is 0, how much will be y? So if I put x 0, this multiplied by 0, it will eliminate, it will go, it will become 0. So if x is 0, if I put 0 here, 0.04 multiplied by 0, it will become 0. So I'll only be left with 0.12y is equal to 2400, and y will be 2400 divided by 0.12, and y will be equal to 20,000 units. Likewise, I want to know if y is 0, how much will be x? So if I put y 0, so 0.12 into 0, it will become 0. I will be left with 0.04x is equal to 2400. X will be 0.4, will go there and divide. 2400 divided by 0.04. X will come to 60,000 units. So now I have both the coordinates for x and y. So when x is 0, y is 20,000. So when x is 0, y is 20,000. And when y is 0, x is 60. This is why when y is 0, x is 60,000 here. So I need to connect these two lines. And here I can write the equation for assembly department, which is 0.04x plus 0.12y is equal to 2400, and this is for assembly department. So I have plotted on the graph cutting and assembly department equations, as you can see. The third constraint is for y. The demand for y is 13,000. Now if you see, this is y, this is 10, 15 will be here. Okay, somewhere here I'm just marking because I'm not using a graph paper, so I'm assuming this is 13,000. Okay, so if I draw a line here, this is y equal to 13,000. That is the demand. Now the next step is, it says establish feasible region. Now the feasible region on the graph is like this. This is 0. This is 1 point. I'm calling it A. You can see an intersection here. O, A, B. You can see an intersection here, C, and this point D. So I can write here feasible region is O, A, B, C, and D. That means within this area, your final combination is. What is the final combination? We want to know how many units of X and how many units of Y we should make and sell so that we can make maximum contribution, maximum profit, even if we have these constraints. The entire concept of linear programming is to find out the combination of products to make, which is X and Y. How many units of X and Y we should be making given the constraint so that we can make maximum profit. So now we need to find a combination, means how many of X and how many of Y should be made and sold so that we can make maximum contribution. So we are doing the graphical method. This is a graphical method, as you can see. So we have to start off with some assumptions, which means trial and error. I'm just assuming here, let's say we are talking about 5,000 units of Y and 5,000 units of X. So look at this line. So this line is known as ISO contribution line. ISO contribution lines or just contribution line. So here we are assuming that this point, if we sell 5,000 of Y and 5,000 of X, we may get maximum contribution. So I am just plugging in the numbers here. See, this is my maximum, this is my objective function. So I'm talking about 0.2 X plus 0.3 Y. So I'm assuming 5,000 units of X and 5,000 units of Y. So 0.2 into 5,000 plus 0.3 into 5,000. Let's see what is the maximum contribution we get. This will be 1,000. 0.2 into 5,000. This will be 1,500. So if I add this, this will be 2,500. This is the contribution. But the thing is, this is our entire region, feasible region. Now the idea is, if you want to get maximum contribution, at the moment it is giving me 2,500. This ISO contribution line has to be moved away. This is origin. It has to move away from the origin to get maximum contribution. So here again I'm assuming, what if I make 10,000 units of, I'm just taking random numbers, 10,000 units of Y and 10,000 units of X. So a contribution line, ISO contribution line will be away from the origin. It's moving like this. Let's say this is the line. So here again, if I write my objective function 0.2x plus 0.3y, this is contribution of 1 unit of x, this is contribution of 1 unit of y. So 1 unit contribution is 0.2. If I'm making 10,000 units of x, plus contribution of 1 unit would be 0.3 if I'm making 10,000 units of y. So how much do I get? This will give me 2,000 and this will give me 3,000. So my total contribution is coming to $5,000. Now look at this contribution line, my total contribution is 2,500. If I take it away, it comes to 5,000. That means I can take it further. Further means it should not cross these boundaries. This and this. This is the feasible region, okay? This is the feasible region. So it has to go away from origin, but it cannot cross the boundary. Here comes experience. As I told you, it is trial and error. I've just done 2 trials, 2 ISO contribution line, moving away from the origin. But my contribution was 2,500, not 5,000. I want to know what should be the maximum. So let me tell you, when you solve this, you are going to do it on a graph paper. And on graph paper, you will be very precise and accurate. Here I'm just showing you the concept and how to go about. So excuse me for some inaccuracy, but I'm giving you the gist of my experience. Remember, out of your feasible region, O, A, B, C, D, this is O, this is A. Okay, so O at O means Y at O here means X is 0. And if I take point A, this A is 13,000. So X will be no units of X and only making 13,000 units of Y. And I told you, we want, non-negativity. We want more units of X and Y. This should not be 0 or negative. So it means that we want to make some units of X and some units of Y. Now here I would like you to understand the importance of non-negativity constraints. X and Y both should be either equal to 0 or greater than 0. But based on experience, I am telling you it should be greater than 0. Greater than 0 means we want to make some units of X, some units of Y. We don't want to make 0 units of X and many units of Y, or 0 units of Y and many units of X. Which means we want to produce X and Y both, but in some combination. So at point A, this cannot be our answer because here we are making 0 units of X and 13 units of Y. Likewise, D cannot be an answer because D is also a combination, because at D, Y is 0 and X is 40. I don't want Y 0 means we are not manufacturing Y at all. I don't want this combination. I want both, which means A and D is out of question. Because at A, X is 0 and because at D, Y is 0. So we are left with B and C. So if we take it further, obviously we don't have enough time. So I am taking you to the most feasible option. So what I'm going to do now is, as I told you, A cannot be an option because at A we are selling 13,000 units of this and no units of X. This is not an option. D cannot be an option because at D we are selling 40,000 units of X and nothing of Y. So B and C is left. So let's talk about B. So at B, what is happening? We are talking about here. So we are talking about X. I'm writing here at point B. What happens? A and D is not a possibility. At point B, we are talking about X 21,000 units and B means 13,000, Y is 13,000 units. So if I plug in the numbers in the objective function, it's 0.2x plus 0.3y. So 0.2 x 21,000 plus 0.3 y is 13,000. So 20% of this would be 4,200 and this is 3,900. This will give you 8,100. So this is the contribution you are making at point B. At C, this is around 24,000. At point C, X is 24,000. And if I take it here, Y is around 12,000 units. So if I plug in the numbers, I take the same objective function, which is 0.2x plus 0.3y. So let's do it here. 0.2x plus 0.3y. So 0.2 is a contribution of 1 unit of X and we are talking about 24,000 units of X, plus 0.3 is contribution of 1 unit of Y and we are talking about 12,000 units of Y. 20% of 24,000 is 4,800 plus 3,600. So this will be 8,400. So now if you guys notice, when I assumed 5,000 units of Y and X, I was getting a contribution of 2,500. When I assumed 10,000 of Y and 10,000 of X, I was getting a contribution of this. So obviously we don't have time to do for trial and error for different combination. Idea is this ISO contribution line has to move. This is origin. It has to move away from the origin till it touches this line. So I took at point B, see 21,000. This is 21,000 at point B. So I took 21,000 of X and at point B it is 13,000 of Y, but my contribution is coming 8,100. At point C, if I go down, this is 24,000 units of X, and at point C, if I come here, it is 12,000 units of Y, which gives me 8,400. So I told you, based on experience, most of the time these 2 points, one of them could be your ideal combination. So our ideal combination is we'll be making 24,000 units of X and 12,000 units of Y, so that our contribution is maximum. So guys, I hope you have understood the graphical presentation of linear programming. We had multiple constraints. Keeping multiple constraints in mind, we came up with a combination that we are going to make 24,000 units of X and 12,000 units of Y in order to get maximum contribution given the constraints. Now the same solution can be provided through algebraic equations, where we won't be showing this graph, we won't be doing trial and error, we'll be using simultaneous equation, and finding the ideal combination. So let's see how it is done. We have these two equations for cutting and assembly department. So I'm writing them here. 0.06x plus 0.08y is equal to 2400, and 0.04x plus 0.12y is equal to 2400. Let's take this as equation 1 and this is as equation 2. Now please understand, what is written before x is known as the coefficient of x. Before x, the coefficient of x is 0.04. Here it is 0.0x. So what I'm going to do is, I'm going to multiply equation 1 by coefficient of this, equation 2. So this will look like this. 0.04 multiply equation 1, which is 0.06x plus 0.08y is to 2400. So I'm taking equation 1 and multiplying by the coefficient of equation 2. So when I multiply 0.04x, 0.04 into 0.06, I will get 0.0024x plus, this was multiplied here, now this will be multiplied by this. So 0.04 into 0.08 will give me 0.0032y, and this now will be multiplied by 2400. So 2400 into 0.04 will give me 96. Now this has become equation 3. Now what I'm going to do is, I'm taking equation 2 and multiplying by the coefficient of equation 1. So equation 2 is like this. Let me write it with a different marker here. Equation 2 is 0.04x plus 0.12y is equal to 2400, but this is equation 2. I'm going to multiply it by the coefficient of equation 1. So this will be multiplied by 0.06. So 0.06 into this will be 0.0024, I presume. 0.06 into 0.04, yes. 0.0024 x plus, this is multiplied already, now multiplied by this. 0.06 into 0.12, this will give you 0.0072y. Now it will be multiplied by this. 0.06 into 2400, this gives you 144. Okay, now this has become equation 4. Now what we are going to do is, we are going to subtract from equation 4 equation 3. So this is already equation 4. I am writing equation 3 here, and then I'll be subtracting it. Equation 3 is 0.0024 x plus 0.0032y equal to 96. And obviously you have learned in school, you have to change the signs. This is plus, it becomes minus. This is plus, this becomes minus. So plus and minus, this cancels out. 0.0072 minus 0.0032 will give you, it will be 48. So y will be 48 divided by 0.004. So y will be 48 divided by 0.004. Y will be 12,000 units. So if you notice, we were talking about y 12,000. See, this we got through graphical equation. Y is 12,000. Now if y is 12,000, this value of y 12,000 we can put in equation 1 if you want to. Look at equation 1, it is 0.06x plus 0.08y is equal to 2400. Now 0.06x plus 0.08y we just calculated as 12,000. So I'm putting it 12,000 here is equal to 2400. So 0.06x plus 12,000 into 0.08 will give you 960 equal to 2400. 0.06x 2400, this plus 960, when it goes on the other side it will be minus 960. So 0.06x is equal to 2400 minus 960 will give you 1440. X will be 1440 divided by 0.06 and x will be 24,000. So y 12,000 x 24,000, same is the answer we got in graphical equation. So I hope you have understood graphical presentation and simultaneous equation for solving question relating to linear programming. Now this is not all. In linear programming, especially examination questions, you are asked about 4 different terms, some calculations as well. You are asked to calculate, and you are supposed to know what is binding constraint. You're supposed to know how to calculate slack. You're supposed to know how to calculate surplus. You're supposed to calculate and understand the concept of shadow price. So let's address these issues in a different question. First of all, we'll do shadow price because we can use some stuff from here. Shadow price is the increase in total contribution. Look, our contribution is 8,400. So shadow price is the increase in total contribution if 1 unit of limiting factor is made available. For example, if you have a look at equation 1 and 2, we are talking about 2,400 machine hours in the cutting department and 2,400 machine hours in the assembly department. What if we are provided with 1 extra machine hour here? If we get 1 extra machine hour in the cutting department, obviously this calculation will change and you will not get 12,000 and 24,000 as your ideal combination. When 12,000 and 24,000 will change, your total contribution will also change. So we want to know by how much it changes if 1 unit of limiting factor is made available, and then I'll tell you the application of it. Now in order to calculate shadow price, first we need to understand what was our ideal combination before. Our ideal combination was we should be making 12,000 units of Y and 24,000 units of X, and the maximum contribution was 8,400. Now we're assuming that 1 machine hour is available more in the cutting department. So how does it look like? See, this was the equation for cutting and assembly department. So I'm writing this here, 0.06x plus 0.08y is equal to 2,401. Not 2,400, 1 extra hour is available. And assembly department remains the same, 0.04x plus 0.12y is equal to 2,400. Now if I use simultaneous equation as I used before, I want to know whether these changes, and if yes, by how much, and as a result how much your contribution changes. So here again I'm taking this as equation 1, taking this as equation 2, okay, multiplying both the equation by the coefficient of the other equation. So let's take the first one, coefficient of equation 2. So it is 0.04x into 0.06x plus 0.08y equal to 2,401. So when I multiply, I'll get 0.0024x plus 0.0032y is equal to 0.04 into 2,401. This will give me 96.04. This becomes my equation 3. Now I'm taking equation 2 multiplying by the coefficient of equation 1. So it is 0.06 into 0.04x plus 0.12y equal to 2,400. So this will give me again 0.0024x plus 0.06 into 0.12 is 0.0072y is equal to 0.6 into 2,400 will give me 144. This will become equation 4. Now from equation 4 I will minus equation 3. So equation 3 is 0.0024x plus 0.0032y equal to 96.04. So I change the signs. This cancels out. So 0.0072 minus 0.0032 is equal to 0.004y is equal to 144 minus 96.04. This will give me 47.96, and y will be 47.96 divided by 0.004. So 47.96 divided by 0.004, you will get y is equal to 11,990. And if I substitute this value in equation 1, which is 0.06x plus 0.08y is equal to 2401. So 0.06x plus 0.08 instead of y, I am putting 11,990 is equal to 2401. So 0.06x equal to 0.08 into 11,990. This will give me 959.2 equal to 2401. 0.06x 2401 minus, this will go there, and minus 959.2. So 0.06x equal to 2401 minus 959.2. This will give me 1441.8, and x will be 1441.8 divided by 0.06. X will be 1441.8 divided by 0.06. X will be 24,030. Now look, the value has changed. So if I plug in the numbers in the objective function here, 0.2x plus 0.3y, so 0.2 instead of x I am taking 24,030, 24030, plus 0.3 instead of y I am taking 11,990. So 0.2 into 24,030 0.2 will give me 4806, and this will give me 0.3 into 11,990 is 3597. So when you add this plus 4806, you get 8403. Now guys, if you notice, before we were getting 8,400 and now we're getting 8403. So just by increasing 1 unit, we are getting $3 extra. So from this, if I minus my old contribution, which is 8,400, I'm getting $3. This is my shadow price. So why are we calculating shadow price? How much are we willing to pay? We are willing to pay as much our contribution has increased. This was our old contribution when we were making 12,000 units of y and 24,000 units of x, and we had 2,400 hours here, 2,400 hours here. So our maximum contribution was this much. Contribution means profit. So if one extra hour is made available, our profit from 8,400 it goes up to 8,403. So how much is the extra contribution made because of one extra available hour? It's $3. That is the maximum price we want to pay for extra machine hour. Please excuse me for any inaccuracies here, because my job is to make you understand the concept. Mathematics, you all have calculators, you can calculate better than me. So idea is to understand the procedure, how it is done. Idea is to understand the application, what is shadow price and why it is calculated. Now we are left with slack, surplus and binding constraint. So I'm writing a small question to make you understand the concept of slack, surplus and binding constraints. So let's have a look. So with this new example, I'm going to explain you the concept of slack, surplus and binding constraints. So here it says a company makes two products, X and Y. Details are given below. Contribution per unit for X is $5 and Y is 7. So we don't need variable cost. One unit of product X requires 3 machine hours, 16 kilogram of raw material and 6 labor hours. One unit of product Y requires 10 machine hours, 4 kilogram of raw material and 6 labor hours. Constraints are given here. Maximum machine hours available are 330 machine hours. Maximum raw material available is 400 kilograms. Labor hours is available 240 hours and minimum 12 units of Y should be sold. Here we are also given the ideal combination, which normally we find that we should be making and selling 10 units of X and 30 units of Y. We are asked to calculate slack, surplus and binding constraint. First of all, we need to put the inequalities. First of all, we need to establish the constraints. Write the equation for the constraints. Let's see how it is done. I'm going to write the constraint for machine hours. So I'm just writing here machine hours. This is the constraint I'm writing. 3 machine hours of X plus 10 machine hours for Y, and we have less than equal to how many machine hours? 330 machine hours. Then I'm writing for raw material 16 kilograms for 1 unit of product X plus 4 kilograms of 1 unit of product Y, and how much of raw material is available? 400 kilograms, so equal to less than 400 kg. Now coming to labor hours. For labor hours, the constraint is 6 labor hours are required to make 1 unit of X and 6 labor hours are required to make 1 unit of Y, but we have only 240 labor hours available. Labor hours. The constraint is minimum 12 units of Y should be sold. So Y minimum means equal to greater than, we can sell more also, 12 units. And for X, you know the non-negativity constraint, X should be equal to greater than 0. Once we have these constraints set, let's talk about slack, surplus and binding constraints. So let's talk about the first equation for machine hours. We are going to check, are we using 330 hours or less than that? So ideal combination is X is 10, Y is 30. So for machine hours, this is my equation, 3X plus 10Y is equal to 330. So I want to know if I'm making 10 units, so 3 into 10 plus 10 hours, but how many units? 30. So 3 into 10 is 30 plus 10 into 30 is 300. So you have 330 machine hours used. So if you're making 10 units of X and 30 units of Y, you end up using 330 machine hours. How many machine hours were available? 330. And you used how much? Exact 330. If that is the case, we call it binding constraint. Binding constraint. Binding constraint means the number of available hours which were there in order to make your ideal production combination, 10 units of X, 30 units of Y. How many you used? 330. How many were available? 330. So if you're using exactly what were available, this situation is known as a binding constraint. So let's see what is the situation when we come to raw material. So if I'm talking about raw material here, this is the equation, 16X plus 4Y is equal to 400. This is the kilograms available. And now we are making 10 units of X and 30 units of Y. So 16 into 10 plus 4 into 30 units. So 16 into 10 is 160 plus 4, this is 120. So you have 280 kilograms used. How many kilograms were available? 400. But you used only 280. So 400 kilograms minus 280 which is used, you have a slack of 120 kilograms. Slack here means though you had 400 kilograms available, in order to make your ideal combination of 10 units of X and 30 units of Y, you ended up using only 280. So 400 kilograms were available, you used only 280. So how much you're left with is known as slack, and you're left with 120 kilograms. Let's talk about labor hours. I'm doing it here, I don't have space. 6x plus 6y is equal to 240. 6 into x, how many units? 10. Plus 6 into y is 30. So 6 times is 60. Plus 6 3 is 18, 180. 180 in 60 is 240 labor hours. How many labor hours were there? So again, it's a binding constraint. So a binding constraint is when the number of available labor hours were 240 labor hours, and making your ideal combination of X and Y, you ended up using exactly 240. That is binding constraint. If you use less, that is slack. Now let's look at your constraint of Y. You were supposed to make minimum 12 units, but your ideal combination is 30. So when we talk about Y, you were supposed to make 12, but you make 30. So 30 minus 12 is 18. This is known as surplus. Surplus means you were okay making minimum 12 units, but in reality you made 30. So if you make extra, you have surplus. Surplus, please note for surplus, look at this. Surplus will only come when you have equal to more than constraint. Okay, equal to more than, you will have surplus. Slack is possible if you have equal to less than. Means you have maximum 400 kilograms, you used only less. So if equal to less than constraint is there, slack is also possible. Binding constraint is also possible. But if it is equal to greater than, as in this, equal to greater than, then there is a possibility of surplus. So guys, I hope you have understood linear programming. If you have any questions and queries relating to this, make sure you leave a comment. I will reply to your comment. If you're not yet subscribed, please subscribe to my channel. That shows that you value my work. If you like this video, please share it with your dear and near ones so that others can also benefit. Thank you so very much for your precious time. Love you all.